Traditionally, signal processing models for wireless communications rely on the plane wave assumption, whereby wireless propagation takes place through plane waves, all impinging from a direction theta. However, plane waves offer a good abstraction of the physical reality only when the communication range is larger than the so-called Fraunhofer distance, which is inversely proportional to the wavelength lambda. It thus follows that as the carrier frequency increases, entering the millimeter wave or Terence frequencies, the Fraunhofer region will shrink. Also, communication will downscale due to the larger path losses at high frequencies. Their conjunction will push communications into the near-field region, wherein the plane wave assumption decays. In this paper, we combine wave propagation theory and statistical signal processing theory to derive a channel model that is also valid in the near field. Compared to previous works on the near-field propagation, our model is the most general and does not require unconventional mathematics. It is based on linear system theory and Fourier transform, which are in the toolbox of every wireless engineer. We focus on scalar wave propagation, but the same theory applies to electromagnetic fields with polarization. In its most general form, the channel is modeled as a linear and space-variant system, which is fully described by the response h, rs at point r, to a unit impulse or point source applied at point s. To determine the impulse response, we decompose the field radiated by the point source into plane waves through a plane wave transform. This operation is exact and generates a pair of transmit plane wave spectra, upgoing and downgoing, here indicated with a plus and minus superscript. Upgoing waves propagate into the right half space, whereas downgoing waves travel oppositely into the left half space. The same occurs at the receiver, where an inverse plane wave transform returns the channel response at any point r. The two words are connected by an integral operator modeling the angular coupling between transmitter and receiver. The kernel of this operator is a 2x2 functional matrix, accounting for all possible upgoing-downgoing interactions. It can be regarded as the spatial frequency response of the linear time-variant system. Mathematically, this yields the exact plane wave representation of the channel, where we recognize the two plane wave transformations and the angular kernel connecting the two. Instead, for stochastic propagation, we look at statistical signal processing theory, and particularly at the spectral representation of a stationary Gaussian process. As the time bandwidth product grows larger and larger, the Caruana-Loew expansion becomes an inverse Fourier transform of a Gaussian frequency spectrum, h of omega. The spectrum is statistically independent from one frequency to another, and at each frequency, its variance equals the power spectral density S of omega of the random process. Consider now a random channel whose realizations are 6-dimensional spatial fields in the transmit and receive locations. The generalization to stationary electromagnetic Gaussian channel builds upon the space-time duality between the Fourier transform and the plane wave representation, shown at the bottom of the slide. Letting this transmit and receive apertures going large compared to the wavelength, we enter the realm of spectral representation, revealing the structure of the channel spectrum H. Precisely, this matrix has uncorrelated entries. Each one of those has a spectrum that is statistically independent from one direction to another, and at each direction, its variance equals the angular power coupling between transmitter and receiver. This has now band-limited support, which limits the integration domain of the plane wave representation. Our last contribution is the analytical modeling of the angular power coupling S between transmitter and receiver. For example, focus on the upgoing interaction. Here, directional statistics is leveraged to model the angular clusters formed by the scattering mechanism of the channel, which only select a portion of the available plane wave spectrum. If you would like to know more, I recommend you to read our paper published on the IEEE Open Journal of the Communications Society. and its application to minor communications, such as the channel generation via Fourier transform and the Nyquist sampling theorem for electromagnetic channels.